It's great to have Jakob here. He's a principal research scientist at NVIDIA, and he's working at the intersection of machine learning and wireless communication. Probably most of you in the call know him because of his contributions to ML for communications. And today he will give us an introduction on Sionna, I hope I'm pronouncing it correctly, which is an open source library for accelerated 6G physical layer research, which is based on GPU accelerated open source library, basically TensorFlow, and it enables the rapid prototyping of complex communication systems and architectures. I think it's really interesting to have this talk today because many of us are working in related areas. So it's going to be interesting to understand if and how we can use this tool for our research. So Jakob, if audio issues on your side are good, you're good to go.
Can you hear me? I switched.
Yes, we can hear you. We can hear you.
Yeah.
Yep.
Okay, great.
All right.
Yeah. Hey, first, thanks of all for inviting me to present this to Sionna to you, by the way. So it's pronounced Sionna.
Sionna. Okay.
Yeah, I actually thought at the beginning it was Sionna, but then we had some Irish people in the company who immediately said, "Oh, that's Sionna." Like, okay, it relates to the River Shannon in Ireland, actually. So and that's kind of been attributed to Claude Shannon if you want, but it's maybe a bit far-fetched. But that's kind of where the name comes from. Yeah, I mean, I don't know if any one of you has watched my GTC talk a couple of weeks ago. So if this is the case, the slides I have are essentially the same. But I thought that rather than making like a really formal presentation of this, I think we could probably use the time better and have, I give you a less, let's say a less formal introduction, and you can essentially ask questions wherever you want, and then we pause and then can discuss certain things. So don't wait until the end to ask any questions. It's more as an open discussion with one of the people who have developed this thing, actually. So I think they might be able to get much more out of it. Good. Yeah, just let me start. So actually, so I joined NVIDIA almost a year ago, and to kick off 6G research. And at that time, we didn't have an link level simulator in the company. So there were not many people doing wireless research, and we thought, okay, do we stick to MATLAB? Do we take something else? And since I've been doing research using machine learning for the physical layer for a very long time, I knew that we needed also to settle on some machine learning, some deep learning library. And while I was working at Nokia prior to joining NVIDIA, I might already actually experimented developing some link level simulations using TensorFlow. And then we thought, okay, we're going to redevelop a link level simulator for our own research, but now why not make an open source project out of it? Because I can just imagine that many people who want to work in this field, they all have the same problem. You kind of need to interface a link level simulator then with a deep learning library. And then it's kind of often very complicated because you need to switch between tools. For example, for channel simulation, you might generate data sets using one tool, then you use link level simulations, you can do it in another tool, and then you have your deep learning solution, which is even another tool, and just like bring everything together so that you can have a single tool that does essentially everything at once. And it was, of course, very important for us that the link level simulator itself is differentiable, so that you can very easily switch components using deep learning. And that's kind of the bit of the background of behind Sionna and why we developed. Okay, but let's get started. I walked through the slide, but please feel free to ask questions any time. I guess there's not much. Everybody will know all of these topics. I mean, these are just some of the hottest 6G research topic that many of us are working on. Terahertz communications to get order of magnitude higher throughput, reconfigurable intelligent surfaces to kind of allow us to control the radio environment and make a friend out of it rather than an enemy we need to fight. I think many people start now looking into joint sensing communications, what's called integrated sensing and communications, just countless applications for autonomous vehicles, road safety, robotics, and logistics. Then, of course, there's machine learning that are not only changing the way how companies are implementing 5G today, but maybe it will also play a role how 6G will be designed and standardized. And then there's semantic communications, massive MIMO, holographic MIMO, cell-free MIMO, UAVs, and so on. And I just mention all of these topics because I have the feeling that for a lot of these topics, you need actually not only new theories, but actually also new tools that allow you to carry out research on it. So for one, my personal example is reconfigurable intelligent surfaces. I always wanted to start working on it, and so that's an interesting kind of problem, but there was not really a channel model. And so then the question is, how can you actually do research on this without being able to properly simulate the system and evaluate that what you're doing makes sense? That's kind of that's just one of these. And so actually, I believe that we need new tools to do 6G research. Right? To some extent, it kind of sometimes feels to me that we are trying to do 6G research with 4G tools, and I think that that's probably not a good fit. Now, let me explain why I think that we need actually new tools. So if you think about RIS or integrated sensing and communications, you actually need to simulate a specific radio environment for this, where you have a spatially consistent correspondence between the physical location, the wireless channel impulse response, and, for example, a visual input. And this can currently only achieve by either you do costly measurement campaign or you do rendering and ray tracing for the same scene. But there's currently no tool that actually allows you to do both at the same time. Then there's machine learning and neural networks, which will become increasingly important for transceiver algorithm and air interface design. And researchers would certainly benefit tremendously from a link-level simulator that has a native machine learning integration and automatic gradient computation. But such a thing also doesn't exist. And lastly, so if you think about link-level simulations for 6G systems, they require unprecedented modeling accuracy and scale. So if you want to simulate a large cell-free or very large aperture MIMO system, this requires quickly a lot of compute power and memory, because of the large number of signal propagation paths that you need to model. Or for example, if you want to model a realistic terahertz communication systems, so channel model and also nonlinear hardware impairment, these simulations become quickly very complicated. And also the full potential of machine learning can only be seen once we do very realistic simulation that actually account for detail that we typically ignore for simulation complexity and mathematical tractability. And so all of these requirements are new, and I don't think that there's any tool that caters for it properly. And that's why we have developed Sionna. And so Sionna is a GPU accelerated framework for next level generation link level simulations. So what GPU accelerated means is actually it's based on Tensorflow, which is an open source deep learning library, like I said, many of you know. And which just, if you have a GPU available, it just runs much faster. But if you have a CPU, it will just work fine, but much slower. So that's what's meant by actually GPU accelerated. So this is really a tool that is developed by researchers, like me and my colleagues, for other researchers, for the community. And its main purpose is just to make our daily work easier. So it's kind of the tool that we wanted to have for a very long time, And I hope that other people enjoy working with it as much as we do. So it's designed to do really rapid prototyping of complex communication systems, which allow you to go as quickly as possible from a research idea to a first proof of concept. So ideally, you have an idea, hey, why don't we look into this or try that? And ideally, in an hour, you should already have an idea if this makes sense or not. And so for this reason, Sionna provides a wide range of state-of-the-art components that you can simply connect with each other to build sophisticated end-to-end link layer simulations. When I say here components, it means essentially Keras layers. So Sionna is implemented on TensorFlow, but using the high-level Keras API. And every component that you can connect is actually a Keras layer. So it doesn't make a difference if you have a neural network layer, like a convolutional layer, or if you have a 5G LDPC encoding layer. It's all the same. So due to the way it's implemented, it has native support for machine learning, which means that you can very easily replace traditional processing blocks by neural networks. As I said, it has so it's differential end-to-end and has native GPU support, but also runs on a CPU. And so you can scale your simulations if you want to do something really large. So you can either split a model across multiple GPUs, or you replicate the same GPU setup multiple times. And this would then just allow you to do essentially much larger batch sizes to simulate things faster. And for those of you who are used to write for loops to do your Monte Carlo iteration and then wait a couple of hours to actually get a result, I think you will see quite a difference. So it will actually be a game changer. So I can't stand when, if I need to wait like an hour for a result, I get a bit impatient. So now you can do these simulations, and most of the time in a couple of minutes you have your result. And this allows you to iterate much quicker and get actually much better results. So we have put a lot of effort into the API design. Somehow I've lost my mouse. Okay. Which is supposed to be very easy and intuitive to use. So everything is fully documented on our websites. You get reference to the papers. Whenever it makes sense, we try to immediately provide the mathematical equations, not just a description of what it does, but actually write down the math, because I think that's much more precise. And so since the entire software is open source, so it means you have always full access to every implementation, and this allows you to build your own components very easily just by extending existing ones. So all of the components we have are very carefully tested so that you can fully rely on them for performance benchmarking with your own algorithms. And we think that that's also a huge time saver, because you can actually focus on your research rather than re-implementing things that your research is not about, or that just might be outside your area of expertise. Just an example, I'm not a channel coding person, but typically you want to evaluate your algorithms with coded bit array performance. That's what's mattered ultimately. And now I can just essentially add 2 lines of code, and I can evaluate whatever I've done, for example, for MIMO processing or for neural network enhanced receiver designs. I can just evaluate it with the state-of-the-art 5G channel code on top. And that just makes my research more credible and impactful with essentially no additional work. And I think many of you might know the story. You submit a journal paper, and then the reviewers tell you, yeah, why didn't you evaluate on coded bit array? Or why didn't you evaluate on, why did you use the radial block fading channel or not a 3GPP kind of channel model? It's much more realistic. And then most of the time the answer is, yes, it would be interesting future work, but out of the scope, right, for this paper. And with Sionna, there's actually no excuse for doing this anymore, because it just you change a couple of lines of code and you can make a much more realistic evaluation of what you have done. And lastly, I think that's the best part. So Sionna is free to use, fully open source. Everything's on GitHub. So we are at NVIDIA, we are further developing it, maintaining it. But we hope that our openness will lead to more reproducible research in our community, and inside many people to contribute components to make, and make their Sionna-based research results available to others. Are there any questions so far?
I do have a question, but I don't know if you're going to address it later. So when you mention like scalability in terms of GPU, do you have a sense of like how many resources does one encoder, a neural network, a modulator block, for example, takes on a GPU? So like how large are these models and how much resources do you need to run them?
Okay, so
but if you're going to talk about it later, no worries.
No, I don't have specific examples for this, but I think it's a good question. So typically, if you have a GPU with 12 GB of RAM, that brings you a long way. For example, you could run let's say a 16 times 4 multi-user MIMO simulation using like a 3GPP channel model where you simulate everything in the frequency domain. Okay, that's very important, because you can, as soon as you want to do the full time, as soon as you do not suppose that you have OFDM, so meaning you with any impairments, that means that you need to compute the full time domain convolution. And that makes, and if you do this and you don't model the channel immediately in the frequency domain, then this makes things much more complicated, and you need a lot of more memory. So that really depends. So then it depends on what is the bandwidth you want to simulate, how long, how many OFDM symbols, for example, you want to simulate. So typically, if you just want to simulate, for example, one slot, 14 OFDM symbols, and you don't go crazy where you want to simulate 100 megahertz of bandwidth, but you maybe go down to, I don't know, 12 resource blocks or something like this. This you can easily do on a single GPU. But if you wanted to do multi-cell simulations with full time domain convolution, then you probably need a couple of GPUs to even fit the model, because the model doesn't fit on a single GPU anymore. Or you would need to go to very low batch sizes. So that's always also the thing. So if you just can have a batch size of 2 or 4, then things will probably not be so fast. But this really depends. So it's hard to tell. And then I will speak about this later. It also depends in which mode you execute your graph. So TensorFlow allows you have the eager mode, where you can essentially experiment a bit like using NumPy. So you just write code and immediately get the result. But then there's the graph mode, where we actually instantiate the entire computational graph in memory and then run it. This goes much faster and also consumes a bit less memory, because you do not store intermediate results. And then there's a third option, it's called the XLA, and this really tries to fuse as many kernels as possible together. So, and this typically shrinks memory usage quite a lot. For example, I just mentioned this 16 times 4 MIMO setup. So I think we have an example notebook. When you run this without XLA, it would probably need 24 GB of RAM. If you run it with XLA, you go down to 4. So that also really depends.
I see. Yeah, thank you.
I also have another question. So you mentioned channel coding and also different channel models. So is everything that you're supporting standard compliant, or are you also supporting some general algorithms that are not necessarily used in 5G or 4G?
Yeah, good question. So we do not aim at all to be 5G compliant. So that's really not the point. That brings me actually to the next slide. So that is a research tool. So we don't want to have it's not like another implementation of the MATLAB 5G toolbox or something like this. So, but we think that to do good research, if you want to do something that's better than 5G, you should be able to benchmark against some of the components. And so, for example, we have implemented the 5G actually specifications for the LDPC and polar codes, so including rate matching. So this is really 5G compliant. So you can take anything from the standard, any modulation coding scheme, it's in there. We have implemented the full 3GPP 38.901 channel models. So most of you maybe know TDL, CDL, but then the more essentially realistic UMA, UMI, and RMA channel models. So these are actually used by, if you make a 3GPP contribution, then typically you are expected to use these channel models. So that's kind of this 5G compliant part, but anything else is really not 5G compliant. So we haven't implemented like a branch channel or the push channel or anything like this. And we also have, for example, if you work with OFDM, we have defined you can use a slot structure, which is very similar to what 5G would define, but it's really not compliant. So just design your grid. You can use any type of pilot pattern you want, but it's not 5G compliant. I have some issue here. I don't know if it's a fire alarm or something. I hear this noise. I need to check.
Yeah, no problem.
No, it was actually a tumble dryer. That's when you work from home. Yeah. So I think I've just let me, but I now glossed a bit over these. So we have a fairly extensive forward error correction module, LDPC and polar codes from 5G. There's also support for read-Muller and convolutional codes, and there's quite a variety of channel decoding algorithms that you can use. So you have of course belief propagation, but then for polar codes you have successive cancellation, successive cancel-list cancellation, and successive cancel-list with CRC. So Viterbi decoder, interleaving scrambling. And I think for me the coolest part is actually the rate matching, meaning you can essentially define any number of information bits and block lengths you want, and it automatically gives you this. So you don't need to try to fit kind of the block lengths into whatever your OFDM grid allows you to do. So typically in the past I've always had this problem that, okay, I need the 916 quam 16 symbols, but I have a code that only gives me block lengths of, I don't know, 1000. So how do I do it? And now thanks to rate matching, that's not a problem anymore. Then concerning channel models, as I said, what's very important is that you can either do the full time domain convolution, and that's really needed if you want to simulate very quickly fading channels that might actually, where the channel impulse response actually varies across the duration of an OFDM symbol. It's also relevant when you want to simulate a system without cyclic prefix, for example, where you need to model inter-symbol interference, then you really need to do the full time domain convolution. But if you want to, so if you just say, okay, I don't care about this, I don't want to model these types of imperfection, you can just do the frequency domain processing. That's typically much faster. And now the reason why we've implemented these 3GPP channel models, which has been a huge amount of work, is actually that in the past, we generated huge data sets from these models using other implementations. For example, there's this great Quadriga channel simulator that I used a lot in the past. But then we always had this issue that you need to use it to generate your data sets. You store them somewhere, then you need to load them in TensorFlow to simulate communications over it. And that was kind of slowing things down. And now you actually don't generate a data set anymore. You just simulate these things on the fly. And that just makes it much faster and much easier to experiment. But for those people who have actually like to work with data sets, for example, either you have it from ray tracing or measurements, you can also, there is a layer that allows you to load data sets and then just, instead of using these stochastic channel models, just load channel impulse responses from your data set to simulate communication over it. Then we have support right now for multi-user MIMO, even multi-cell user MIMO, where you can find some antenna patterns also from the 3GPP specification. There's a simple zero-forcing precoder, LMMSE equalization. And for OFDM, there you can essentially do whatever you want. So arbitrary pilot pattern. We have just implemented for now a simple least square channel estimator where you do nearest neighbor pilot interpolation. So there's a lot of room to do something better, but actually a solid baseline, which is not too far away from what you find in many products. Good. Now I would like to spend a bit of time to explain you some design principles of Sionna. So as I've said, most parts are written in Python using the Tensorflow Python API. And all individual components, such as decoders, channel models, MIMO detectors, and so on, are actually Keras layers. And that means you can simply connect them in the same way as you would build a neural network. And for this reason, it's very easy to mix traditional algorithms and neural network component. So the other advantage, of course, of this design decision is that you can get automatically the gradient computation for an entire system from end to end for free. And therefore, you can think about Sionna as a fully differentiable linked level simulator. Maybe I use this moment also to address a question that we get quite a lot. So why have we not used Pytorch instead of TensorFlow? And so there are two answers to this. One, it's personal preference and experience. So most of us who have developed it have years of experience with TensorFlow. But since TensorFlow version 2.0, I would actually claim that the API of Pytorch and TensorFlow is more or less identical. So if you would replace TF by Torch, your code would almost run. But the main reason is actually that we really wanted to use Keras, and there's currently no high-level API that has the same kind of community support for Pytorch. So that you didn't see such a high-level API for Torch that has yet emerged. So there are a couple of competing APIs that are emerging, but we couldn't find one that we liked as much as Keras. And so that's the main reason why we actually use TensorFlow. And we also believe that anyone who can write something in Pytorch might take 1 hour to get familiar with how you would write it in TensorFlow, and that shouldn't be an issue. Good. So another design principle is that all algorithms in Sionna are expressed as operations on high-dimensional tensors. Though the first dimension is always the batch size, and then you could have, for example, the number of transmitters, receivers, antennas, the number of the M-timbals, FFT size, and so on. But the precise dimensions after the batch size really depends on what you're simulating. But the crucial thing is that there are essentially no for loops in the entire source code where you would iterate it across any dimensions of a tensor. And this leads to embarrassingly parallel workloads that you can very efficiently execute on GPUs. So the batch size dimension comes now, of course, from the field of deep learning, but you can think of it in Sionna as the number of simultaneously executed Monte Carlo trials. And the limiting factor for the batch size is generally the GPU memory. But if you say, okay, I have a second GPU available, you need to just double the batch size without any work at all. So you get this for free as soon as you just have more hardware. Now, since we deal most of the time with complex valued numbers on the physical layer, so we have decided that TF complex 64 is the default data type. So it means that each complex dimension is represented as a 32-bit floating point number. And while this precision is enough for most use cases, there are some components where high precision is really needed. An example is channel models for optical communications. So this will be one of the new features coming up in a couple of weeks. Is the split step Fourier method to simulate optical channel models. And there you really need much higher precision. So therefore, in every layer, we can just change the data type to TF complex 124 so that all internal computations are done using this precision. Now I mentioned this already at the beginning. So you can use all of the TensorFlow execution modes, either in graph execution and also this experimental TensorFlow feature called Accelerated Linear Algebra, or XLA. However, with XLA, the issue is that not all kernels you have support this. So an example is, for example, the FFT. I think the FFT with complex 128-bit support doesn't run in XLA mode. The same holds for the I think for the matrix inverse. There's also an issue that we have circumvented, but it's still under development, so it can change any time. So I just wanted to mention that this is experimental. And yeah, and lastly, you can also write your own custom TensorFlow operations in C++, XLA, or CUDA. And that might be beneficial for operations that are difficult to express using the existing TensorFlow operations. So an example would be the checkload function for min-sum decoding, or even the time domain convolution. So when you want to compute a convolution of a sequence with a time varying filter, this is fairly difficult to express with the current TensorFlow API. And it would actually be much easier to implement it with a custom CUDA kernel. Now, implementing your own custom ops is a bit more involved, but it can provide significant speedups. And so we have done this for a couple of operations, and we will put soon a tutorial on our website so that you can see how you do it if you want to. Now let me walk you through a simple Hello World example, just to get an idea of how coding with Sionna looks like, where we simulate the coded bit error rate of a 5G LDPC code over a simple AWGN channel. So that's really a Hello World example. So you would typically start by defining a batch size, so 1024. I want to have code words of length 1000 with 500 information bits, meaning we have a rate 1/2. Then we use 4 bits per symbol for the modulation, so it means we have a 16 QAM, and we want to simulate at an SNR of 10. So here it's 10 dB, but it's the same linear scale, right? So the next thing we do is we instantiate the required Sionna components and then just connect them in the desired order. So here I do something that I don't do typically when I code, but I just put it here for the example to make it simple. So I used what is called the functional API of Keras to set up a model where you essentially you instantiate an instance of a class and then immediately apply it. So for example, I create here a binary source, and then I immediately generate from it a tensor of size batch size times k. And I do this, and then I have an LDPC encoder with the given number of information bits and the block length, and I immediately apply it to the outcome of the binary source. And then the map the coded bit stream to constellation symbols. So that is where I use this mapper object that actually uses the constellation object, which is a QAM with 4 bits per symbol. Then I apply some Gaussian noise. We have a Gaussian B-mapper, and then which computes the LLRs, which will simply then be used by the decoder to compute an estimate of the information bits. Now, depending on your GPU in such a model, you could go to crazy batch sizes. So I think even you can do a batch size of 100,000 without any problem for this, or even 1 million. And this means essentially when you execute this code once, you simulate in parallel 1 million code word transmission. And so it means essentially you get a coded bit error rate curve by executing your graph, I don't know, 10 times. And that's really super fast. Okay, so now a very nice feature now of Sionna is that you can make some components trainable or replace them by neural networks. So here in this example, I have made the constellation object trainable, meaning now these are considered as trainable weights of your now it has become essentially a neural network, right? It's a computational graph which has some weights that can be trained. And I've replaced the B-mapper by a neural network. So this could now just be another Keras layer or Keras model that implements a neural network of your choice, which now computes LLRs. And so now if you want to train this thing, so you would need to define a loss function. For example, here I've just said, okay, I'm interested in the binary cross entropy between the information bits and the kind of the soft bits that come out of my decoder. And then I wrap everything into a gradient tape. And now TensorFlow can compute us with this tape gradients function, the gradient of the loss function with respect to all of the trainable variables. So it would be the constellation as well as the weights of my neural demapper. And now you could use these gradients for example, for stochastic gradient descent to update your model parameters. Now I have here a live demo, a video, but I won't show it because I cannot synchronize my voice to this video, and I think it would also be a bit long. You can find this on the internet. I think on the landing page of our documentation, you get access to the video if you want to have a look. So I will skip over this. Okay, then let's go to the next slide. So if you want to get started, I think the best way is really to have a look at our webpage. This is where you find the installation instructions. There's a quick start guide. There's a full searchable API documentation. Maybe I can just show you this. So now I think I don't know what I'm sharing now. So
Yeah,
I shared some. Am I now sharing a browser?
yes.
Yeah. So this is for example, this is how the website looks. Yeah, this is video I mentioned about if you want to get a 1-minute teaser about how to use it. But I think what most people use most of the time is the API documentation. So for example, if you want to learn how are the channels implemented, here's where everything is actually explained in huge detail with equations, links to everything. And so one very nice feature, if you're browsing through it and you're interested, okay, how is a flat fading channel model implemented? You can just click on the source button and you immediately see the source code and you can switch between the things. So that's sometimes very useful if the documentation is not enough. And then we have actually a huge range, and that's expected to grow over time, of tutorials. So really starting from the basics, and then there are quite a few notebooks for experts who speak about different types of channel coding. How do I do realistic multi-user MIMO simulations? How do I load channel models from data sets? And so on. And so you can either see the notebooks directly here, or what's also nice, you can just run them immediately in Google Collaboratory. If you want to give it a try. So now it's open in Colab and you can execute it and play around with it. So that's probably the easiest way to get started. Yeah, good. So now I go back to the to these slides. Okay, yeah, I mentioned these notebook tutorials. Yeah, it's quite a lot there. So hopefully there's something for everyone in there. So actually, I think it should become clear that you can use Sionna also for non-machine learning based research. So it's actually even when you want to work on coding or just on MIMO detection, you can actually do this. If you don't have any trainable components, it's also fine. And then lastly, so if you have any questions, there's the GitHub forum, which is really a good source for help, where you can ask questions, propose new ideas for features, and so on. Now, as I've mentioned a couple of times, I wanted to explain to you how and under which conditions you can contribute to Sionna. So first of all, Sionna is released under the Apache 2.0 license. And we have chosen this for the great freedom it offers, and for people, especially in companies, not to worry about patent infringements and litigation. So I think that's a great open source license that essentially allows use in academia and industry alike. So we welcome contributions from third parties. The typical way is through pull requests, and the process looks roughly as follows. So you create a fork of the GitHub repository. So fork is essentially, it will be it's always an open repository that cannot be private. That essentially just mirrors what's going on in the actual repository. And now you can, for example, you create a new branch in your fork saying, hey, feature one, and you write your code, you document it using doc strings, and that's very important because we generate the entire API documentation automatically from doc strings. You add a couple of unit tests if needed, and then you submit a pull request of your branch of the fork to the GitHub main repository. And then some of the maintainers will then review this pull requests. Possible there's some discussion going on or some code modifications, and then ultimately will be merged into main. And so there is no contributor license agreement. This has essentially been replaced by signing off all of your commits with the developer certificate of origin. So this ECO essentially replaces this contributor license agreements, and it affirms that you have written the source code and are allowed to submit it to the project. So this is as easy as just essentially adding this -s flag to any commit. So it will just add essentially a line saying signed off by John Doe at something. So that's very easy. But before, actually, if you want to contribute something that not just a bug fix, it's a bigger component. So the best thing is actually to reach out to us prior to start the development, because there are a lot of components currently under development, and this is to avoid that we have duplicates, or you would like to develop something that's already partially planned. So just have a discussion prior to this, so that you are not wasting any of your time. Now, another way to contribute is actually just to file bug reports or feature requests. This can be done through the GitHub issues. And for any type of question that you don't find answered on the website or forum, or that you don't want to ask publicly on GitHub, you can also send an email to sionna@nvidia.com. And the last thing is, so there's one more cool feature that we plan to release very soon. And I think that's very important. And so I'll just give you a small look into the future now. And that's ray tracing. I think I mentioned that a lot sometime. There are, I think, many research topics in 6G that really require ray tracing. And because you want to have this physically consistent modeling of a specific radio environment. And this cannot be done with any of the stochastic channel models. And sometimes you want, on top of the ray tracing for wireless, you also want to get a visual representation of a scene on top of the simulated radio propagation. And so right at the moment, we're developing Sionna RTX that will bring both of these capabilities directly into Sionna, so that you can essentially render a scene, get the channel impulse response, and use it immediately for link level simulations. And that from within a Jupyter notebook without the need for any other software, and with just a few lines of code. So, and then there's kind of the same name. So Sionna RTX embraces NVIDIA's RTX architecture for hardware ray tracing. And this is also based on the material definition language, which is I would say, the industry standard for defining and sharing physically based materials. So ultimately, Sionna embraces the compute, AI, and ray tracing cores for really fast simulations of 6G systems. And that's all I had. I just wanted to give credits to some of the alpha testers we had to make the first release what it is today. And yeah, I hope that this tool is of interest to some of you. If you want to get started, pip install Sionna. That's the only thing you need to do. Yeah, and I think then we now have time for some questions or discussions.
All right, thank you very much. Very, very interesting talk. Any questions from the people that are online? Yeah, Mauro, please go ahead.
Hey, hi. Can you hear me?
Yeah.
Yes.
Okay. Hi. So, yeah, first of all, great presentation and yeah, great work. I think I can speak with everyone in this chat here. This is the tool we were waiting for, you know, especially for people watching.
That's what I like. That's what I like.
Yeah. No, because basically the very first thing you said is about, okay, you as a researcher in wireless communication and also in machine learning, the first thing you want to do is to maybe use MATLAB to generate your code and then port everything to, Python frameworks, and that's a very long and like a path full of troubles, as everyone has experienced. So that's great. No, so my question is, so this is all simulation, and that's great. I mean, I'm a computer scientist. I love simulations, but at some point, in our research, we also want to try this thing, with physical, real world transmissions. Is at any point on the roadmap for this tool, do you have in mind to include also interfaces to, I don't know, use, for example, USRTs, like software-defined radios, to be connected as blocks, of this, part of this graph that you can implement in this tool?
Or if I can add to this,
yeah, definitely.
The NVIDIA Aerial platform. Any
Okay.
plans?
Great question. I mean, I have done myself a lot of software-defined radio implementation. I always felt that that's the most convincing thing you can do ultimately, right? You need to demonstrate that it works with real hardware. So that simulation bring you so far, but at some point it's more convincing to do. So definitely. Now comes the thing. Sionna is not supposed to be used for real-time communication. So it won't be something like GNU radio. So it will not support real-time communications where it's, where you stream things and you do video streaming of something and do real-time experiments. Definitely not. That's not how it's architectured, and it will be too slow. So it's really not optimized for this. So it's really a simulation tool. However, we have done this also in the past. Nothing prevents you from doing something that's close to real time. So meaning you use Sionna to generate your waveforms. Then you just feed it to the UHD driver to actually transmit it over the air.
Yeah.
Then you record it, and then you record it, and you do if it's slow enough, you can do the processing in real time.
Yeah.
But it's really not, we don't aim to allow you to do like, you can 100 megahertz of bandwidth communication. So, but for example, so this type of scenario where you would say, I would like to do end-to-end learning over the air, where I transmit, I don't know, 100 waveforms over the air. I record them, process them to generate a loss, maybe do some neural network training, updates weights, and then you iterate over this many times. That's definitely planned and possible. And so we work with an academic partner on providing some interface for USRP. So that's coming, but it's definitely not going towards GNU radio. So it's not real time. And now you brought up Aerial. So if you wanted to really do real time experiments, then you would probably need to go to something much more complex, like Aerial, or something else. I don't know if that answers the question.
I see. Yeah. That definitely answers my question. I mean, I see your point for real time. Definitely, like you need completely different architecture, probably like a
totally
ad hoc
so you
design.
wouldn't use TensorFlow for this, and you would probably memory, so it's
absolutely, yeah. You need to get more closer, probably to.
And there's also
bare
the
metal
thing that
instruction.
Sionna is fast for simulations because of these large batch sizes that you do in parallel. So if you want to do now real-time processing, you don't have you have batch size 1. And so
yeah, I agree.
That's why it's not a good fit. So you need to architecture differently. So but definitely one has support, like at least some nice interface from Python, which makes it easy to send and receive actually waveforms that you've generated with Sionna over the air. I think that's something we definitely want to do.
Okay, thank you.
All right, Paolo. We cannot hear you, Paolo. No. We have some techniques.
Otherwise, just write your question in the chat.
Can you hear me?
Yes, we can.
Okay, I'm from another, from a colleague's phone. Sorry for that. So thank you for the very interesting talk. I've been working on ray tracing myself for some years, and I've always wanted to use the RTX libraries, but it's out of my skills. So that's really great that some contribution from NVIDIA is coming, and I'm looking forward to it. And also, I think that the key for this framework is the slide about contributions, because you said that every component is implementing the state of the art, but with so many fields put together in a simple framework, the state of the art moves quite fast. So it's often the case that you get a simulation tool which is not really updated, and it's difficult to update every single part on by yourself. So that's really great. And on that side, I wanted to ask you, I didn't get if I wanted to contribute, do I have to do it in Keras? I mean, if I want to contribute at the high level API. Or just Keras, or do I need to use, or can I use any tool in Python?
Oh, so it must be ultimately what you need to provide is a Keras layer. So that definitely, because otherwise we want to keep everything, it must be like all of the other blocks. So, and now the way you implement your Keras layer is typically using the TensorFlow Python API. Or, I mean, if you are really deep into it, you could even write your own, submit your own custom TensorFlow kernel and do this. Yeah, that's it. But it couldn't be, so you can't make it if you now say, hey, I have a block written just in Python, for example, using NumPy. So the thing is, this could even be a contribution because there are just some things that cannot be implemented in, or are very difficult to be implemented using the TensorFlow API. And there's actually a way to wrap, for example, NumPy or any Python code into a Keras, or into a TensorFlow code. So it can be, and I think an example is, I haven't implemented the FEC package, but I think we have one example. I think there's one, I think the successive list cancellation decoder with CRC. I think that's not written in TensorFlow. I think that's written with using NumPy, and then it was just wrapped to make it look as if it was a Keras layer. And so that could also be a contribution. I mean, in this case, you don't get automatic gradient computations through it, but it's still usable as a reference for others. So you could, as a benchmark or something like this, so it would still be interesting. So not all components need to be fully differentiable. Sometimes it just doesn't make sense.
Okay, that's perfect. Thank you very much.
Hi, I have a quick question. Can you guys hear me?
Yeah.
So has there been any work or any attempt at using Sionna or simulation like this for reinforcement learning workflows, maybe to develop some kind of like a custom environment using these blocks, or is this mainly for supervised, unsupervised, like inference type tasks?
So we haven't done much using reinforcement learning, but there's nothing that would prevent you from doing it. And there's one example where we actually do, I would say, poor man's reinforcement learning. So there's an example notebook where we do gradient estimation. We essentially compute a policy gradient through the channel. We just assume that the channel is a black box, as if you would do experiments using a software-defined radio, and you can't get gradients through it. And then just we implemented a policy gradient to estimate the gradient of this black box and run this. So, we don't use any other framework to implement in the reinforcement learning parts. We wrote it ourselves, but you could in principle do it, but we haven't written any high-level functionality to do it. So I think it would be cool. So, for example, I especially think about the next step if you go now to if ray tracing will be there, and then when we want to start doing some, let's say, more high-level optimization using reinforcement learning, then this would definitely need to play a bigger role. But so far, we haven't done much with it. But it's definitely an interesting area.
Thank you.
All right. Any other questions? We're also at the top of the hour.
That's great. So I just wanted to say something. What I really hope for is that some people write a paper where they use Sionna and make a nice Jupyter notebook that generates you the figures of your paper. And then so what we right now we are thinking about how this could be done, but we plan to have on the website essentially something like, I don't know, maybe called Made with Sionna, where essentially people can just contribute either notebooks that explain more like in a tutorial style, like a blog where you explain something, or you say, hey, this is the Jupyter notebook for my latest paper. I think that would be really cool and would help our community a lot if we had more reproducibility.
Yeah, I think that help reproducibility. I see that Mauro has another question. I don't know if it.
Yes.
Yeah.
Hey, yeah. Sorry, just a quick one. Jakob, you mentioned in the beginning, I think, of the talk, the bit error rate analysis, for varying SNR levels in the simulation. And you said that, there was an easy way after defining all the components of the simulation to have that. So I guess there is some sort of wrapper that, gets this graph that you define for the simulation and run this graph over multiple transmission for different SNR levels. Is there any example for that? I don't want to.
Yeah. So the basic idea is always that you define ultimately a model, like a Keras model, where you say, the model has a call, right? It takes some arguments as inputs and produces some outputs. And the inputs could be batch size, SNR, or whatever parameter actually you want to iterate over. So, and then you have a model where the input, let's say input is SNR and output is, I don't know, code, actually information bit ground truth and coded or information bit estimation, or directly the bit error rate for this batch. Then you have the model. And then, for example, we have one function that's called simulate bit error rate that takes as input this model and an array defining all of the SNR points, and then it just loops over it, and then you get the result. But so we have many notebooks that do the same thing for various settings. So ultimately, you always want to construct a model, and then that you can just execute many times for many different parameter settings or inputs to do these simulations. And using that's why the model is important, because then it's also very easy to distribute your workload across multiple GPUs, because for TensorFlow, this is just a Keras model, and you can use all of the nice TensorFlow features for distributed training and interference.
Yeah. Because I I was thinking exactly about, more like distributed simulations, or like heavily, parallel simulation, as this tool is intended for, right? So like in the
Can be
beside,
very
like,
small. It can do everything, so that's a nice thing. So you can
yeah,
use something small on your laptop, but you can go crazy on your DGX SuperPod.
yeah, and we have some from NVIDIA, so thank you for that.
Okay,
All right,
that's
thank you.
good. I actually need to move on to another meeting.
Thank you very much.
Thanks. Yeah, also thanks for your interest. I hope it resonates with you, and I look forward to hearing about your Sionna success stories, or also things you don't like. Any type of feedback is very welcome.
Sure, we'll send you feedback.
Okay.
All right. Thank you
Bye
very
bye.
much.
Have a great weekend. Bye.
Thanks, everyone. Bye-bye.
Thank you. Bye-bye.